From the sound processing perspective, the cochlea works as a set of bandpass filters. So that means that the cochlea is divided into many parts which respond to different frequencies. So low frequencies produce oscillations near the apex, and high frequencies they produce oscillations near the base or the oval window. So this figure here shows the behavior of the traveling waves of different frequencies along the basilar membrane for the complex tone, which are presented simultaneously and propagate from the oval window to the apex. So we see that these traveling wave envelopes, they occur in response to an acoustic tone complex containing, for example, sinusoids of 400 Hz, 1600 Hz, 6400 Hz. And we see that the peak responses for each sinusoidal are localized along the membrane surface, with each peak occurring at a particular distance from the oval window or the cochlear input. The amplitude of these traveling waves, they gradually increases from the oval window into the direction of the apex and reaches a maximum and fades rapidly beyond this maximum. Thus, the inner ear performs the very important task of frequency separation. Sound energy of complex tone is transferred to, divided and concentrated at different places along the basilar membrane. So this way we see that we can look at the basilar membrane as a filter bank, and this filter bank has highly overlapping bandpass filters. The magnitude response of these filters, they are asymmetric and nonlinear, they are level dependent. So we are talking about non-uniform bandwidths and the bandwidths that increase with increasing frequency.